this section, we'll explore the object-oriented features of Python. But before that, I want to give you a general idea about programming paradigms and object-oriented programming. Programming paradigm is an approach to organize and structure your code. It is actually a style of programming. The two common programming paradigms are procedural programming paradigm and object-oriented programming paradigm, also known as OOP in short. In the procedural paradigm, there is a step-by-step procedure that is followed sequentially for solving a specific problem. It is implemented through code blocks called functions. The program is organized in a way such that the functions process the data of the program. In object-oriented programming, real-world entities or concepts are modeled using objects. An object has both state and behavior, means it contains both data and code to manipulate that data. So in procedural programming, you model your program in terms of functions, and in object-oriented programming, you model your program in terms of objects. Programming languages are designed such that they provide features to support one or more programming paradigms. For example, C is a procedural programming language as it has functions, but it has no features for object-oriented programming. Java and C# are examples of object-oriented languages. Python is flexible as it supports both these programming paradigms, and it is up to the programmers to choose the suitable one according to their problem. You can even mix both the approaches to accomplish your specific task. So far, we have been using procedural approach. We have learnt everything about functions. Now we'll see the object-oriented approach. So in this lecture, we'll see what object-oriented programming is, and then in the rest of the section, we'll see how to implement object-oriented programming in Python. First, let us see the common terms used in object-oriented programming. Classes and objects are the two main components of object-oriented programming. Suppose you are making a library management system. You might want to model different users as objects. Each user will have a name and an ID, and each user can borrow a book or return a book. You will also need to represent different books as objects. So suppose each book object contains title of the book, ISBN number, author name, and a book can be issued or deposited. So we can see we generally need to model real-world things that have similar behavior but differ in their internal state, which means that their data is different. For example, here all the user objects can borrow a book or return a book, but all have their own data. Similarly, all these book objects have similar behavior but different data. When we need to create an object of integer or string type, we can use built-in types. But when we have to create different type of objects that our program requires, we have to define our own type. These new types are called user-defined types and are created using classes. To create these objects, we can define a class called user, and to create these objects, we can define a class called book. A class is a blueprint for creating the objects. A class actually specifies what data its objects will have and what behavior will they exhibit. When we define a class, we create a new type. The values of this new type are called instances or objects of that type. Each object that is created from this class will have this data and this behavior. Creating a new instance of the class is called instantiation. Classes encapsulate state and behavior together. This is called encapsulation. State is maintained through variables, which are also called data members, and behavior is implemented through methods. Methods are like functions, but they are defined within a class. So a class defines what data and methods should the object have, and the objects contain the actual data. And instantiation means creating an object using a class as the blueprint. Now the behavior defined inside the class is shared by all the objects, but data is not. Each object behaves in the same way but has its own data. This means that the methods defined in the class are shared by all the objects, There is only one copy of each method which is used by all the objects, while each object maintains its own copy of variables. So you can think of class as a template that is used to create objects that behave in the same way and have their own data. One of the advantages of object-oriented programming is code reusability. Classes that you define can be used by different applications. Then you can inherit from these classes to make new classes. This reduces development time and effort. Then there is a sort of data security as the data is encapsulated inside the object, and hence there are less chances of it being misused by other parts of the program. You can hide all the inner workings of the class from the user of the class. This hiding of the internal working of a complicated system from its user is called abstraction. Polymorphism, which means one thing many forms, can also be implemented in object-oriented programming. Now in the next lecture, we'll see how to create classes and objects in Python. But before going to the next lecture, I want to clarify the terminology used in Python so that you don't get confused between the terms objects and classes. We know that everything in Python is an object. Integers, strings, functions, modules, all these are objects in Python. When you define a function object is created. Similarly, when you define a class object is created. And these objects that are created from the class are called instance objects or just instances. So Python supports the concept of classes and objects through class objects and instance objects. In this lecture, we'll see the syntax for defining classes and creating objects. A new class is created by writing the classes statement. First, we write the keyword class and then the class name. Conventionally, the class names begin with a capital letter and are generally singular nouns. If there are multiple words in the class name, then they are joined using the camel case convention, where the first letter of each word is capitalized. After the class name, we put the colon. This line is followed by an indented block of statements which form the class body. As in a function definition, all the statements inside the class definition are also indented. Right now, we don't want to add any data or code to this class. We want to make just an empty class. So we'll write this pass statement here. So we have a simple class definition here. Let us execute it and see what happens. So Python has actually created a class object and assigned it to this name person. This is similar to what happens when a def statement is executed. We can see ID of this class object. So like everything else, classes are also objects in Python. They are called class objects. Now let's see how to create instance objects from this class. We can instantiate a class object by calling it like a function. That is by putting a pair of parentheses around it. So when this will be executed, an instance object will be created whose type will be person. Now we assign this object to this name P1. So this name P1 refers to an instance object whose type is person. Let's create one more instance object. So this is another instance object of type person. Now let's execute it. We can see type of P1 and P2. So they're objects of type person. Let's see their IDs. We can see these are two different objects in memory. Both are of type person. P1 is a person, P2 is also a person. Now let's print these objects and see. These values are the addresses in hexadecimal. Here the numbers are printed in decimal. So we have seen how to define a class and how to instantiate it. But the class that we have created is useless as it does not have any data or methods. So first we will add two methods to it. For that we will write two def statements inside the class. We'll write another def statement. So these are methods. These definitions of methods look like function definitions, except that we have this parameter self here. We'll talk about this parameter in a little while. So you can think of methods as functions that reside inside a class. To call a method, we'll write the instance name followed by a dot and the method name. So let's call these methods here. So we have called these two methods display and greet with this object P1. Now let's call these methods with object P2. Let's run this now. So this is how we can execute the methods using instance objects. Now you must be wondering how this code executed without any error, because both these methods have one parameter each. But while calling these methods, we did not send any argument corresponding to this parameter self. This worked because when a class method qualified with an instance object like this is called, Python automatically sends the argument for this parameter self. To see what value Python sends for this parameter, let us print self parameter inside these methods. Let's run this. So this is object P1 and this is object P2. We can see that the object that called the method is printed in the place of self. In these two calls, self refers to object P1 and in these two calls, self refers to object P2. So now we know that Python provides the instance that call the method as the argument for this parameter self. Although you specify this self parameter in the method definition, you don't have to provide a value for it when calling the method. All the methods inside a class should have this first parameter self. We'll see some exceptions later on, but in general, all methods should have this parameter. Python uses this parameter to identify the instance object that calls the method. You can use any other name instead of self, but using self is a convention and it is a very strong convention, so it is better to stick with this name. In the previous lecture, we had seen that classes specify the behavior of instance objects and they define what data the instance objects will have. The behavior is shared by all the instance objects while each instance object maintains its own data. We have added behavior in the form of these two methods, display and greet. Now let us see how to add data. We'll add data in the form of instance variables. We know that in Python, a variable is created by assignment. It comes into existence when it is first assigned. There's no need to declare it. Similarly, instance variables are also created by assignment. So suppose we write here, so this variable name has been attached to instance object P1. This is called instance variable because it is attached to an instance. But this variable has been attached only to P1, not to P2. So if we write here P2.name, we'll get this error. We want all the instance objects to have same variables. So we'll not attach the instance variables like this outside the class. We'll attach them inside the class methods. That way, all instance objects created from the class will have the same set of instance variables. Now you know that inside the class methods, you can access the instance object by writing self. So if you write self dot variable name, then that variable will be an instance variable. It will be an attribute of the instance object. So let's add two instance variables in this class. We'll create a new method here. And here inside this method, we'll create two instance variables, name and age. Now we'll call this setDetails method for these instances P1 and P2. Let's run this. We'll see p1 dot name, p1 dot age is this. So now this object p1 has two instance variables, name and age. Similarly, the object p2 also has these two instance variables. So this is p2 dot name and this is p2 dot age. So whenever an instance object will call this method set details, it will get these two instance variables attached to it. Instance variables are specific to an instance of the class. Every instance has its own copy of instance variables. Changing the value for one instance does not affect the value in another instance. So let's change this p2 dot name. Let's change p2 dot age also. So now this is p2 dot name and p2 dot age is this. Let's check the instance variables of object p1. They were not changed. So each instance has its own copy of instance variables and these variables define the state of the instance objects. Now this method set details always sets the name to John and age to 20. We would generally want to assign different values to different instance objects. So to make this method more flexible, we'll add two parameters here, name and age. And now here we assign name to self.name and age to self.age. Don't get confused in the two sets of names. Self.name and self.age are instance variables, while this name and age are parameters of this method. So they are just local variables inside this method. You can use this name and age only inside this method, but you can use these instance variables anywhere inside the class. This is because these instance variables are attached with the instance object and they live as long as the object lives. They will not be destroyed when the method terminates, as is the case with these local variables. This dot notation makes sure that there is no conflict between the two sets of names. You can use any other name for these parameters, but it is a convention to use the same names as instance variables. So this name and age are instance variables of the self object, while these two are local variables. Now here, when we call this set details method, we'll send two arguments. So now we are able to give different values for name and age. Let's run this. So now this is p1.name and this is p1.age. So the names and ages of p1 and p2 are different. Now let's use these instance variables in these methods display and greet. So here we have written self.name. Now in this method greet, we'll use the instance variable age. So here we have used this instance variable age. When you reference an instance variable outside a class, it has to be prefixed with the instance name and a dot. Inside the methods, self refers to the current instance. So the instance variable name is prefixed with self and a dot. Now let's run this. So we can see the values of these instance variables were used here. So these instance variables name and age are defined in setDetails method and are referenced in these methods display and greet. Now suppose we want to call this method display inside this method greet. When an instance object calls this method outside the class, it is called like p1.display or p2.display. Inside a method, the current instance is accessed by using self. So here we'll call it as self.display. So here we have called this method with self. Let's delete the display calls from here. So from outside the class, we are calling this method greet, and inside this method greet, this method display will be called. Let's run this. So we get this output. So outside the class, the instance variables and methods will be accessed by preceding them with instance object and a dot. And inside the class methods, they'll be accessed by preceding them with self and a dot. So we have seen how to define classes and how to create instance objects. There was a lot of new syntax involved. So in the next lecture, we will summarize whatever we have studied in this lecture. We define a new class using the class statement. And when a class statement executes, it creates a class object and binds it to the class name. Instantiation of the class creates new instance objects. To instantiate the class, we have to call the class object with a pair of parentheses. The instance object is like any other object of Python. It can be used as an element of a list, tuple, dictionary, or a set. It can be passed to a function as argument or can be returned from a function. Even class objects are first class objects in Python. They can also be passed as argument or returned from a function, can be bound to variables, or used as an element in a container, or can even be attribute of an object. Methods are defined inside the class using the def statement, and they follow all the rules that we have studied in functions. Inside the method definition, the first parameter should be self. You don't have to provide any argument for self while calling the method. Python will automatically assign the instance object that calls the method to this parameter self. This parameter is always required so that we can access the instance variables and methods of an instance object from within the class. Instance variables can be created inside any method by assigning to a variable name prefixed with self. If you have worked in Java or C++, you must have noticed the difference in how these variables are defined. In these languages, these instance variables, which are also called data members, are statically declared. They are a formal part of the class definition. While in Python, they are defined inside methods, and it is possible to even dynamically attach instance variables. To reference an instance variable inside any method, again you have to prefix the variable name with self. To call a method inside another method, you have to prefix the method name with self. So outside the class, we must use an instance object name in front of methods and instance variables. And inside the class, we must use self in front of the methods and instance variables. Many programmers who are used to other languages like Java or C++ generally forget to include self as the first parameter in the methods. If you forget to do this, the interpreter will complain. Let's remove this self from here and see what error is shown. So Python shows this error. Set details takes 2 positional arguments, but 3 were given. Here we have sent 2 arguments, but it is saying that it received 3 arguments. This shows that Python automatically sends an argument. And so we always need to specify self as the first parameter. And after that, we can have a regular parameter list. So let's put self back here. Another mistake that beginners in Python make is to forget to prefix the instance variables and methods with self. So if you forget to put self here before this method name and run this, you get this error. Name display is not defined. This display is a method of the class, so it should be called with an instance of the class. And we know that self refers to the current instance inside the class. So you need to call it like this. If you forget to use self for an instance variable inside a method, then also you will get an error. So suppose you forget to write self here before this instance variable age and run this, you get this error. Name age is not defined. So you need to prefix all your instance variables with self. Now suppose we define another method. Inside this method, we want to change instance variable age to 75. But again, we forget to put self before this instance variable age. Now we call this method for this object P1. Let's run this and see what happens. We expected an error, but the program ran without any error. Let us see P1.age. It was not changed to 75. Let us see what happened here. An assignment was made to this name age. And we know that in Python, a variable is created when it is first assigned. So here Python created a local variable named age with value 75. And this is why we did not get any error. Now let's write self here. And again we run it. And we see P1.age. Now it has changed to 75. So you need to remember to write self whenever you have to use an instance variable or a method name inside the class. We have seen this class in one of the previous lectures. Whenever we create a new instance object for this class, immediately we have to call this method setDetails. Because when this method will be called, then only the instance object will have its instance variables created. Now suppose we forget to call this method for this instance object P2 and we directly call these methods display and greet. We run this program and we get this attribute error. For object P1, we had called the method setDetails, so its instance variables were created. But for object P2, we forgot to call this method, so its instance variables were not created. And here we have called these two methods on P2. Now this method wants to access instance variable name of object P2. And this method wants to access instance variable age of object P2. But these instance variables were not created for this instance object. So we get this attribute error. So if you forget to call this setDetails method or you call it after calling any of these two methods, you will get an error. You always have to remember to call the setDetails method immediately after creating any person object so that the instance variables are created and can be used in other methods. Now it is definitely cumbersome to call this method every time we create an object. Python has a solution for this. It lets you automate this task. So you can define a method named init with 2 underscores before and after this name init. This method will automatically be called after the instance has been created. So if you have any code that you think should be executed just after the object creation, put that code inside this method. Now for this class, we want this code to be executed after we have created the instance object. So let's change the name of this method to init. Now this name is not a convention like naming of self. This is a special name and you cannot choose any other name for this method. And the two leading and trailing underscores are also important. Because of these underscores, this method is generally called dunder init, where dunder is a short form for double underscore. Now let's delete this call from here. We don't have to call this init method explicitly. Python will call it implicitly. So now you must be thinking, when we don't have to call this method, how will we send the arguments for these parameters name and age? These arguments will be sent here when the object is instantiated. Now let's run this. So we get this output. This dunder init method was called automatically. So when you create instance objects, any arguments that you pass to the class are passed to the dunder init method. And like other methods, it also should have this self parameter. So we have seen that the initialization work is automatically done by Python if you define the dunder init method. You can create and initialize all your instance variables in this method. Although instance variables can be created in any other method also, it is more readable and clear if you create all the instance variables in this dunder init method. You can also perform any other startup task that you want in this initializer method. For example, opening a file or setting up a network connection or connecting to a database. Like other methods, the first parameter is always self. And after self, other parameters that are coded are used to give initial values to instance variables. These parameters can be given default values also if required. These types of methods that have special names and have double underscores before and after their names are called magic methods in Python. The magic is that they are not called directly. They are called automatically in certain contexts. We'll learn more about these methods later in this course. If you have worked in other object-oriented languages, you must be thinking about constructors right from the starting of this lecture. The dunder init method definitely looks like a Java or C++ constructor, but it would be technically incorrect to call it a constructor of the class, because by the time this method is called, the object is already constructed. To construct an instance, this magic method is called. So technically, this is the actual constructor. As a beginner, you won't need to use this method much. It is generally used to code meta classes. This dunder init is the initializer method. It is called immediately after the instance is created. It is the first method that is called on the newly created instance object. The self parameter passed to this method refers to the newly created object. So this method does not construct the instance object. It initializes an already constructed instance object. You can have only one initializer method in a class, since there is no concept of function overloading in Python. However, it is possible to create your instance objects with different types of data using class methods that we'll see later in this course. Some languages implement data hiding in a class by declaring the data and methods as private or public. Private data and methods can be used only by the methods inside the class, while public data and methods can be accessed from outside the class as well. So this part of the class can be used inside this class only. In Python, there is no such concept of private or public. First, let us see why there is a need of this distinction between private and public when working with a class. The users of a class are generally called clients, and the client code uses the class by instantiating it, that is, by creating its objects. So suppose we have these three clients that use this class named product in their applications. These clients can access this variable data3 and can call these two methods, method x and method y, through the instances of the class. But they have no access to these variables and these methods. The creator of the class has chosen to hide them from the user because these things are used in internal working of the class. They are not required by the user. For example, in a car, you have access to steering and brakes. You don't need access to all the internal parts of the car that make your car move or stop. Those internal details are best left to the creator of the car. If you get access, you might inadvertently damage something and the car will stop working. Similarly, in a class, only those parts are exposed to the user which are required. Other internal details are hidden in the form of private variables and private methods. This part that is visible to the user is the interface of the class, and this part is the implementation. The interface of the class generally comes with a guarantee that it will not change with time, but implementation may be changed without any warning. So a private method or a variable may be deleted or its behavior can be changed without any notice. These changes may be done to fix some bugs, to change some functionality, or maybe to improve efficiency. Any change in implementation does not affect the client code because client is not using the implementation part. It is not concerned about how the class is doing its work. It just gets its work done by calling these public methods. If we again take the car analogy, the internal parts of the car may be changed or can be made to work in some other way, but your steering and brakes will work in the same way. So the interface is generally not changed. Now let's come to Python. In Python, everything inside the class is public. Clients can access any data or any method. So if these clients use this Python class, they are free to call any of these four methods and they can access any of these data variables. Python does not enforce any access restrictions on data and methods like Java and C++ do. However, there is a naming convention that is used to indicate that a certain attribute is meant to be used inside the class only. You can use a leading underscore on an instance variable or a method to suggest that it is private and should not be used outside the class. These variables and methods are technically just like any other variables or methods. They can be accessed outside the class also, but the leading underscore indicates privacy. This way you can discourage clients from using the private things of a class. However, you cannot stop them from doing so. So Python works on the policy that we are all consenting and responsible adults and know how to use the code. Its philosophy is based on the trust that users of the class will respect the convention and documentation and use the methods and variables appropriately. One of the reasons for making everything accessible outside the class is debugging. When you need to fix a bug, you have to sometimes access the private attributes of the class. So if you prefix a variable or a method with a single underscore, then it indicates that this name is non-public. It is only for the internal use of the class and should not be accessed outside it. If you prefix a name with double underscores, Python will do some name mangling and that attribute will not be directly visible from outside the class. For example, this is internally replaced with this name, where my class is the name of the class in which this attribute is defined. These names are mangled by prefixing with a single underscore and the class name. So these names are not directly accessible from outside the class, but they can be indirectly accessed. So if you use a name that starts with at least two leading underscores and has at most one trailing underscore, that name is mangled by Python and it cannot be directly used by the user. This naming can be used for your non-public members of the class to make it difficult for the user to access those members. But this name mangling mechanism is not there in the language for this purpose. Its purpose is to make the name specific to the class so that there is no name clash with subclasses. To indicate privacy, you should use a single leading underscore. Then there are names that start and end with two underscores. We have seen one such name, dunder init, and we'll see many more. These types of names are used by Python for its internal use, and we should not write our own names that have double leading and trailing underscores. A single trailing underscore is used to avoid name clashes with Python built-in names. For example, if you want to use the name class or range in your program, you can use it as class underscore or range underscore. It is best not to use these built-in names in your programs, but if you ever need to do so, the convention is to use a trailing underscore. Now let's go to idle. We have this class name product in which we have these two variables and these two methods. This variable and this method are prefixed with an underscore, which indicates that they are not supposed to be used outside the class. Let's run this now. We can access data1. We can call method A. This underscore data2 also can be accessed outside the class. And this underscore method B can also be called. Although these attributes are prefixed with an underscore, it is possible to access them outside the class. For Python, this underscore does not make any difference. It is just a convention and programmers should respect this convention and not access these attributes like this outside the class, unless there is some need for debugging or something like that. Now let's change these single underscores to double underscores. Let's run this now. Now this attribute cannot be accessed. and this method cannot be called. Let's call the dir function on this instance object P. We can see that the names of these two attributes have been mangled. They have been prefixed with the class name and an underscore. So we can access these attributes with these names. So we cannot directly access these attributes from outside the class, but we can access them indirectly. Inside the class methods, these variables can be accessed directly. In this lecture, we'll see how to define a property and why we need to define one. When we define a property, we add a new attribute to the class. First, let us see the syntax with the help of an example. We have this class where we have these two instance variables and this method display. We define another method and inside this method we are just returning the value of this variable underscore x. Let's run this. We can call this method like this. Now here before this method we'll add a line at the rate property. Now after adding this line, this name value has become a property. We can access it like we access an instance variable. Let's run this. Now we write p dot value and we could access the value of this variable underscore x. So the code of this method was executed, but there was no need of putting the parenthesis here. You could access it as if it was an instance variable. This at the rate property is a decorator. We'll learn about decorators later on. So when we decorate a method with this line, that method can be accessed like an instance variable instead of as a method. We can use this p dot value in an expression like this. So by defining this property, we have added a new attribute that can be accessed like an instance variable. We can see this new attribute using the dir function. So we can see this new attribute here. Now let's try to assign something to this attribute named value. We got this attribute error. So although a new attribute has been defined, we can only reference it. We can't assign anything to it. For that, we have to define another method, and in that method, we'll write the code that will be executed when we assign something to this attribute value. So now here we define another method. Name of this method is also value. It takes one parameter after the self. And inside this method, we have this one line of code. Now the important point here is that we have to put one line here. So now whenever we assign anything to this attribute value, this method's code will be executed. The value that is assigned will be the argument for the second parameter of this method. Let's run this. So now we were able to assign to this attribute named value. So whenever we'll reference this attribute named value, this method will be executed, and whenever we'll assign something to it, this method will be executed. This is the getter method and this is the setter method for this property. This name should be same in both the methods, and the setter method accepts an argument which is used for setting the property. Now let's create one more property. Name of this property is y. So this is the getter method for this property. Let's write the setter method. So when you reference this y, this method will be executed, and when you assign something to this, then this method will be executed. In this method, we are returning the value of variable underscore y, and in this method, we are setting the value of this variable underscore y. Let's run this. So you can see that by defining this property named value, we are referencing and assigning to this variable underscore x. And by defining this property named y, we are referencing and assigning to this variable underscore y. So you can reference or assign to the property using the syntax of an instance variable. But under the covers, the method code is getting executed. Now after seeing the syntax, let us see why we need to use properties. We have this class person with these two instance variables name and age and this method display. Now suppose after some time you want to ensure that whenever age is assigned a value, that value should be within the range 20 to 80. One possible solution could be to make age a private variable and define a set age method in which we can put the validation code. So let's do this. We make this age a private variable by prefixing it with an underscore. Here also we change it. And now we'll define the set age method in which we'll change the value of age. So this is the set age method. We are raising a value error if the new age is not within this range. Now this underscore age is a private variable. So client is not supposed to access it directly. So we have to define a getAge method also. So now when the user wants to change the age, he'll do it through this setAge method and the data validation will be done. Let's run this. So it did not allow us to set this age. Again we got this error. This time the age was within the range, so we did not get any error. And the age was changed. So this update in the class successfully implemented the new restriction on age. Now suppose the user wants to increase the current age by 1. So first you'll get the current age using this method getAge, add 1 to it, and then you'll send this value to setAge. So the age was increased by 1, but this statement looks very awkward. And there is still a problem in this code. When the user creates a new object, he can send any value for the age because there is no data validation done in the initializer. For example, we create a new object here. So we need to put the data validation in the initializer also. So now we have put the data validation in this initializer also. Let's run this. Now we create this new instance and it showed us this error. So now the data validation is done here also when we create a new instance object. Now this code works, but it is not Pythonic. We are repeating the same code at two places, and another problem, which is a big one, is that it breaks the existing client code. There may be a lot of client code that access the attribute age directly. All that has to be changed. For example, this client code will not work now because the instance variable is now underscore age and not age. So here the client has to change this p.age to p.setAge and this p.age to p.getAge. So our new update is not backward compatible. It breaks the interface. The Pythonic way of going about this whole thing would be to create a property. So this time let's create a property to add the data validation for attribute age. We had this person class previously. Now instead of the setAge and getAge methods, now we'll create a property here. Now we'll define the setter method. So in this setter method, we have put this data validation. So now we can easily access age as an instance variable and the data validation is also done. Let's run this. We can access age like this. This age was within the range, so it was changed. We did not get any error. This was outside the range, so we got this error. Let's create a new instance variable. We did not change the initializer, but the validation is done here also. It is done because this property method is called here. Since age is now a property and we are assigning to age here. Now, if we have to add 1 to the current age, we can easily do it. Or we can write. You can see this is much more concise and cleaner than it was using the set age and get age methods approach. Now let's run the existing client code and see. So this code is also working smoothly. No changes need to be done in this existing code. So your changes to the class are backward compatible. So when you need to perform some data validation on an existing instance attribute, you can turn it into a property. Another use of property is that you can make an instance variable read-only or write-only. If you provide only the getter method, not the setter method, the property becomes a read-only property. Let's see this with the help of an example. Here in this class, we have defined three properties: name, password, and salary. For this property name, we have defined only the getter method. We have not defined the setter method. So this property becomes a read-only property. This attribute name is read-only. This attribute password is write-only because in this getter method, we have raised this attribute error. If you provide both the getter and the setter methods, the property becomes read-write property. So this attribute salary can both be referenced and assigned to. It is a read-write attribute. Now let's run this. This name attribute is read-only. If we try to assign something to it, we can't. We get this error. Then this password attribute is not readable. We get this error, password not readable, but we can assign to it. This salary attribute is both readable and writable. We can read it and also write to it. So property allows you to make an attribute read only or write only. Let us see one more example of using property. In this rectangle class, we have these three instance variables: length, breadth, and diagonal, and two methods, area and perimeter. The value of this instance variable diagonal is computed from the values of these two instance variables, length and breadth. Let's run this. We create a new instance. Let's see the diagonal. This is the value of diagonal. This is the area. And this is the perimeter. Now let us change the length. Now let's see the diagonal. Diagonal has not changed. Now the area is this. And the perimeter also shows the changed value. So area and perimeter have changed because they are implemented as methods. But this diagonal has not changed. So if you change the value of an instance variable, any other instance variable that is computed from it will not automatically update. So here in this class, if we change length or breadth, diagonal will not change accordingly. Now one solution could be to implement diagonal as a method, but then we'll not be able to access it as an instance variable. Whenever we want to access it, we have to put the parenthesis. This will also break existing client code who have used diagonal as an instance variable. So the solution is to turn it into a property. So let's change it to a property. Now this diagonal is a property. So now we can continue to access diagonal as an instance variable, and whenever we'll access diagonal, we'll get the updated value. Let's run this. We create a new instance object. Diagonal is this. Now we change the length. Now we see the diagonal. Now the diagonal has also changed. And there is no need to define the setter method for this property because we don't expect the user to change the diagonal. This is the first example that we had seen in this lecture. Now, in addition to the getter and setter methods, we can also define a deleter method for the property. This deleter method defines what happens when a property is deleted. To create this deleter method, you have to define a method with the same name as the property and add this decorator with this word deleter in it. So when we'll delete this attribute, this method will be executed. Let's run this. Now we write del p dot value. So this method was executed. Now let us summarize whatever we have learnt about properties. A property allows access to an instance variable through methods, even though the method syntax is not used. Using the property syntax, we can define methods that are automatically called when an instance variable is referenced, assigned, or deleted. For getting a property, you need to write this line just above the method definition. For setting a property, you have to write this line, and for deleting a property, you need to write this line. The names of these methods are same, and all of them take self as the first argument, and the setter method takes an additional argument for setting the value of the property. You can use a property for attribute type checking and validation. You can create a read-only or write-only attribute using property. You can transform an instance variable into a dynamically calculated attribute. You can incorporate new behavior in your instance variables without any need to rewrite the existing client code. So you can use a property to give new functionality to existing instance variables. So you can start implementing your class by coding your instance variables as public, and in future if you need more control over any instance variable, you can change it to a private attribute and write a property to access it. This way there will be no change in the existing code that uses the class. Now in the property getter and setter methods, don't perform actions that are surprising or take much time. Referencing or assigning to an attribute is something that the client will expect to run instantly. So it is not advisable to run other helper methods in the property methods. If a task is very complex and time consuming and may have side effects, consider putting it in a separate normal method. We have seen how instance variables are created and used. These variables are stored in different instance objects so that their values can be different in each instance object. The instance variables are created and referenced inside methods using this self parameter. Now let us see what is a class variable. A variable that is assigned at the class level, that is outside any method, is a class variable or a class attribute. Let us define a class variable for this person class that we had written earlier. This variable named species is defined inside the class but outside any method. So it is a class variable. A class variable is shared by all the instances of the class. It belongs to the class, not to individual instance objects. The data of a class variable is stored in the class itself, while the data of instance variables is stored in individual instance objects. The species will be same for all the person objects. There is no need to have a unique copy for each instance. So we have defined it as a class variable. These class variables are generally placed at the top of the class definition, just below the class header. Now a class variable can be accessed using the class name or the instance name. Let's run this. We can write this, or we can write this, or we can write this. So we can see that the class variable is the same whether you access it with a class name or with an instance name. You can't access an instance variable like this with the class name. For example, you cannot write person dot name because each person instance object has a different name. There is no name attribute attached with the person class itself. But you can write person dot species since species is the same for all the person instance objects. Now let us use the id function to see that all these three references refer to the same variable. So we can see the IDs are all the same. So they all refer to the same class variable stored in the class object. In fact, the class variables can be accessed even before any instance object is created. Inside the class methods, you can access a class variable by preceding it with the class name or self. Let's use this inside this method. Let's run this. We could use self also here, but using the class name clearly shows that it is a class variable. Then we can use a class variable to count the number of instance objects created. So let us add one more class variable here in this class, and it will store the number of person instance objects created. So now here we have added one more class variable named count and initialized it to 0. Now in this initializer method, we'll increment count by 1. So whenever a new instance object will be created, the value of this variable count will be incremented. Let's run this. The value of this variable count is 2 since we have created two instance objects here. Let's create two more objects. Now let us see the value of count variable. Now it is 4. So if you have some information that is applicable to the class, not to each instance object, then you can make it a class variable. Let us see one more example. We have this bank account class that has these instance variables: account number, owner name, and balance. Now the rate of interest would be the same for each instance of the account. So you can make it a class variable. A bank can charge some fees if the balance becomes less than a minimum amount. So you can make a class variable for minimum balance and for minimum balance fees. These things will not vary for different accounts, which means that they'll be the same for all instances. So we have defined them at the class level. You can use these class variables in the different methods that you define for the class. For example, you can check for this minimum balance after a withdrawal in this method. If there is an instance variable that has the same name as the class variable, then the instance variable hides the class variable if you access the name through an instance. So here in this class, we have this class variable named x, and we have this instance variable also named x. Let's run this. This gives us the class variable, and this gives us the instance variable. So when we access a name through an instance, Python first checks whether the instance contains that variable. If the instance does not contain that variable, then it checks the class to see if there is any class variable. Now inside this method display, self.x means the instance variable x, because we are accessing x through an instance. If we want the class variable x, we should precede it with the class name. So this prints the instance variable x, and this prints the class variable x. We have seen that we can access a class variable using either the class name or the instance name. But if you try to change the value of a class variable using an instance, then something unexpected occurs. Let's see with the help of an example. In this account class, we have this class variable named rate, and we have these two instances of this account class named A1 and A2. We can access this rate using class name or any of these two instances. Now let us change the value of this variable using the class name. This has changed to 6 now. Let us see a1 dot rate. So a1 dot rate and a2 dot rate are also showing 6. Now let us change the value of this class variable using this instance variable a1. Let us see a1 dot rate. This is 7. Let us see account dot rate. This is still 6. Let us see a2 dot rate. It is also 6. This statement did not change the class variable. It actually created a new instance variable for this instance a1. For proof, we can check the IDs. So we can see that this ID is different. So if you want to change a class variable, you should use a class name. Otherwise, a new instance variable will be created. Similar thing will happen if you change the value of a class variable inside a method using self. So for example, here we have this method. Now in this method, we are printing self.rate and account.rate. Both will print the class variables. These IDs will be same. After that, we write this statement. This will not change the class variable. It will create a new instance variable for the instance that calls this method. After that, we print self.rate and account.rate. Self.rate will print the newly created instance variable and this will print the class variable. These IDs will be different now. Let's run this. So we can see IDs are same here and different here. So from this output, we can see that this statement created a new instance variable. If we need to change the class variable, we should do it using the class name. So now we write here the class name. Now let's run this. So now we can see that the class variable was reassigned. The methods that we have been defining till now have self as the first parameter. And when they are called, they automatically receive the current instance as the first argument. These methods are more precisely called instance methods to distinguish them from the class methods and static methods that we are going to study now. So when we simply say methods of a class, we generally mean instance methods because the other two are not as frequently used. So now let's see what are class methods. Here we have defined a class method. A class method is a method that is associated with the class itself, not with any particular instance of the class. To make a method a class method, we need to add this line before the method definition. It is a function decorator about which we'll study later on. So if you add this line before the method, it becomes a class method. Like instance methods, class methods also have a special first parameter. The first parameter in a class method is named CLS. You could write any other name here instead of CLS, but just like self, this name CLS is also a strong convention. This word is a short form of class. Since class is a reserved word, this word CLS is used. So in an instance method, the first parameter is self, and in the class method, the first parameter is CLS. When you call this method, you don't need to provide any argument for this parameter. Python will automatically send the class as the argument for this parameter CLS. A class method can be invoked using the class name or an instance. So let's invoke it using the class name. We have not created any instance of the class, but still we could call this method because the class method has nothing to do with instances. When this call will execute, Python will automatically send the class as the first argument. So this parameter CLS refers to the class object. And that is why here inside this method, we have accessed this class variable A through CLS instead of hard coding the class name. Let's run this program. So this method was executed and the value of this class variable A was printed. A class method can work only with the class variables. It can't access instance variables as it does not have a self parameter. So if we have to make a method that needs to use only the class variables, we can make that method a class method. A class method can also be invoked using an instance, but it makes more sense to invoke it using the class name. Now let us add a class method to the person class that we have made in the previous lecture. So here we have this person class. Let's add a class method to it. So first we'll write this line at the rate class method, and now we'll define the method. Inside this method, we have used these two class variables, count and species. Now let's call this method here. And again, we'll call this method here after creating two instances. Let's run this. So we got this output. We could call this method here using any of these two instances. So let us write here P1. So this also worked. We get the same output, but calling with class name is definitely more natural. So when you have to process some information that is associated with the class itself, not with any instance object, you can turn your method into a class method by writing this decorator and specifying CLS as the first parameter. The most common use of class methods is to define factory methods. Let us understand it with the help of an example. Again, we take the same person class here. I've deleted the class variables to keep it short and simple. We can create a new instance object of this class by providing name and age. There may be situations when we want to create instance objects of type person from different types of data. For example, we may have a string that contains name and age separated by a comma, or we may have a dictionary that contains name and age. You might read this type of data from a file or from any other place. Now you want to be able to create an instance of type person from this string also and this dictionary also. Python does not support function overloading, so there can be only one type of initializer. We cannot have more than one definitions for init method inside a class. So to add this functionality to our class, we have to rely on class methods. So here we'll add a class method. CLS as usual is the first argument, and after that it takes a string. We are splitting this a string to get this name and age. Now we'll create a new instance here. We know that inside the class methods, the CLS parameter refers to the class object. So CLS here refers to the person class, and writing this will create a new person instance object, and this init method will be called. And now we return this newly created instance object. Now here we'll call this class method. This string is sent as argument to this method, and the instance object returned from this method is assigned to this name P3. Now we'll call the display method. Let's run this. So we were able to create a new instance object of type person from this string. Similarly, we can make a class method to create a person object from this type of dictionary which has name and age as keys. So let's create another class method here. So here we are sending the values of the dictionary as argument to this person class initializer. So both these methods are calling the same init method. Now we'll call this class method here. This dictionary D is sent as the argument. Now we call the display method. Let's run this. So now we were able to create a new person object from this dictionary. So class methods allow us to provide alternative initializers for our class. These are called factory methods. We can use class methods as factory methods to create instance objects in different ways. Now suppose we have this employee class and we want to create a person object from an employee object. This employee class has first name, last name, birth year, and salary as instance variables. Let's import the employee class here, and we have an employee object here. Now we'll create a class method named from employee. Employee object has first name and last name as instance variables. And in person class, we only need name. So we add these two to get name. And to get age, we subtract the birth year from the current year. For this, we have to import datetime class from the datetime module. After finding this name and age, we send both these things to the person class initializer. And then we return the newly created instance object. Now we'll call this method. Let's run this. So we could create a person object from an employee object. In this lecture, we'll see what are static methods. We can see the syntax of defining a static method here. To make any method a static method, we have to put this @static method decorator before the method. You can see that unlike instance methods and class methods, a static method does not have any special first parameter. It can have regular parameters, but the first parameter has no special significance. So when a static method is called, Python does not send the class object or the instance object as the first argument. And this is why these methods can neither access the instance object state nor the class state. So when you have to create a helper or a utility method that contains some logic related to the class, turn it into a static method. For example, in the state class, you can write a method isLeap that can be used as a helper method in other methods of the class. So if you have to make a method that needs to access instance variables, make it an instance method. If you have to make a method that needs to use only class variables and not instance variables, make it a class method. And when you need to create a method that needs to use neither instance variables nor class variables, then make it a static method. Such a method depends only on its argument values. A static method is just like a regular function, but it belongs to the class namespace. We know that the definition of a class defines a separate namespace. And when you want to group functionalities under the class namespace, you can create static methods. Static methods are like normal functions. So instead of defining a static method, you can define a module level function that is defined near the class. So if you have a single class per module or only closely related classes in a module, then you can make a module level function instead of writing a static method. In this lecture, we'll see what are magic methods. We had created this fraction class earlier in our exercise. Here we have these two fraction objects. Let us try to add them using the plus operator. It did not work. We got this type error. Similarly, we'll get an error if we try to multiply these two fraction objects using the multiplication operator. So again, we got this error. Then here we have defined this add method to add two fraction objects. So now let's use this method to add these two fraction objects. So now we got the sum. If we use this method multiply, we can use it to multiply these two objects. So we can make our instance objects behave in any way by defining different methods. But if we want them to behave like built-in type objects, we need to define methods with special names. And why do we want our instance objects to behave like built-in objects? So that there is a consistency in the interface provided by the built-in classes and the user-defined classes. Being able to multiply or add two fraction objects using these operators is much more convenient than using different method names. So when we define a class and we want the instance objects of that class to respond to some Python syntax, we need to define some special methods. These special methods begin and end with double underscore. They are sometimes called dunder methods due to the double underscore added before and after their name. These are some examples of some dunder methods. We are already familiar with this dunder init. It is the most commonly used dunder method. It is called automatically by Python to initialize a newly created instance of the class. These methods are also called magic methods as they are run automatically by the interpreter when an instance object is used in a particular syntax. These special methods are generally used to overload operators, built-in methods, and some other built-in functionality. By overloading an operator, we tell that operator to behave differently depending on the type of its operand. We've already used this concept of operator overloading when we used addition and multiplication operators with numeric types and strings. This plus operator knows that when its operands are numeric type, it needs to add them. And when operands are sequence type, it needs to concatenate them. Similarly, this operator, when used with numbers, means multiplication. And when used with sequences, means repetition. We can use these two operators with instances of our class if we define these two methods inside our class. So now let us go to idle and define these methods for our fraction class. Let us add two underscores before and after this method name. So now we have this dunder add method. The first parameter as usual is self, that refers to the object that invokes the method, and the second parameter is conventionally named other, and we create a new fraction object inside this method and return it from this method. Now let us call this method. First we'll create two fraction objects. So we have called this dunder add method here like this. But the magic is that now we can write this f1 plus f2. The syntax f1 plus f2 is converted to this method call internally. This method is called on object f1 and f2 is sent as the parameter. And the return value of the method is the value of this expression f1 plus f2. Python did this magic for us and it will do this translation only if we use this spatial dunder name. So when Python will see plus operator working on a user-defined type, it will look for dunder add method in the class and will invoke it if it is present. Now let us add a magic method for subtraction. The code for it will exactly be the same as this one, except that we'll have a minus here. So let us copy and paste this code. The name of the magic method for subtraction is dunder sub. And now we can subtract an integer or a fraction from another fraction. Now let's make this also a magic method. So now whenever we'll use a multiplication operator between two fraction objects, this method will be called. Now let's run this. We have these two fraction objects. So we could use the subtraction operator. Now let's use the multiplication operator. We can use the multiplication operator also. So now we can use addition, subtraction and multiplication operators with our fraction objects. So these special methods are generally not called directly like this in the code, but they are called automatically when the related syntax is used. These are some magic methods that we can define in our classes. These methods can be used to overload arithmetic operators. These methods are used for overloading comparison operators. These three for overloading unary operators. And these methods can be used to make your instances work with built-in functions. And these are for customizing instance creation and deletion. By defining these magic methods, you can specify what should happen when instance objects of your class are used with Python operators and built-in functions. For example, when you define this dunder add for your class, you are actually specifying the behavior of your instance objects when they are added. By default, most of the operators and built-in methods will not work with the objects of our class. We generally get a type error when we try to perform an operation that is not defined in the class. So when we define our own class, we have to decide what type of operations we need our class to support. For example, when making a class fraction, we would like to overload arithmetic operators, but not for person or employee class. There is no sense in adding or multiplying an employee object by another employee object. Then you can write any code inside the definition of these methods, but the code that you write should not be totally unexpected. For example, you should not write code for subtracting two fractions in the dunder add method, although it is possible to do so. But it makes things confusing for the user of the class. There are many other magic methods also. You can check Python documentation for a full list. We'll discuss some of them in this course. In this lecture, we'll see some more magic methods. These are the magic methods for comparison. We'll define them for our fraction class. We can compare fractions by cross multiplying. For example, if we want to compare these two fractions, we cross multiply. This side we get 7 and this side we get 6. So this one is bigger. Similarly, when we compare these two fractions, we find that they are equal. Now these two operators are available for every class that we define. So first let's see what happens when we compare two fractions by using these two operators. This is our fraction class and here we have these two fraction objects f1 and f2. Now we write this. The value of these two fractions is same, but still we get false here. This is because by default for every class, two instance objects will be considered equal only if they are same object. Otherwise they are considered unequal. So this f1 equals f2 gives the result of f1 is f2 and this gives the result of f1 is not f2. So if f1 and f2 refer to same object, then only this expression will return true. Otherwise, it will return false. So according to default implementation, any object is equal to only itself and not to any other object. If we want to compare our instance objects in some other way, we need to define some magic methods. So now let's provide our own implementation of equality. So this is the dunder method that will be called when double equal sign will be used with fraction objects. Let's run this again. Let's create some fraction objects. Now we check this f1 equals f2. And now it returns true. Let's check f1 equals f3. This is also true. Let's check f1 is not equal to f2. We can see that the behavior of this operator has also changed. So it is not necessary to define the dunder any method if we want it to just behave as the opposite of this dunder EQ method. Now let us define the behaviors of less than and less than or equal to operators. This method dunder LT overloads the less than operator and this method dunder LE overloads the less than or equal to operator. Defining both this dunder EQ and dunder LT methods does not mean defining the behavior of less than or equal to operator. For that, you have to define this method separately. Let's test these operators now. First, we'll create some objects. This gives false. This gives us true. F1 is less than F3 is false. F3 is less than F1 is true. Now let us see these two magic methods that are used for converting an instance object into a string. This method is used when an instance object is used with the str built-in function and when the instance object is printed using the print function, because print implicitly calls this built-in str function. And this method is invoked by REPRA and interactive echo. And if this dunder str is not defined, then this method is invoked for stra and print a also. Both these methods return a string representation of the instance object. This one is generally used for the end user of the class. It returns a high-level user-friendly and readable representation of the object. And this one is a descriptive and unambiguous string representation of the object. It is there to be used by programmers for debugging. It is generally a valid Python expression from which you can recreate the instance object. Now let's go to idle and define these two magic methods for our fraction class. So again, we have this fraction class and here we have this fraction object f. We get this string containing the class name and the object ID. The interactive echo will also give us the same output. And this strf also gives the same string. If we want to display the fraction object in fraction form, we need to use the show method that we have defined here. So now we get it in this form. Now let us define the dunder str method for this fraction class. And now let's run this. Now let's check printf. So now printf prints the object in this form. And now you don't need to call this show method. This strf also gives us the same string. Let's check the interactive echo. This still gives the same output. So now let's define the dunder repr method. So now here we have defined this dunder repr method. Let's run this again. Let's check the interactive echo. So this used this dunder repr method. Containers like lists and dictionaries will use dunder repr for string representation of the contained objects. So suppose we have 3 more fraction objects. And we have a list of these 3 fraction objects. Now we print this list. So this calls the dunder repr method. Now let us look at this method dunder del. We know that Python performs garbage collection to free up memory space, which means that it automatically destroys objects that are no longer in use. When the reference count of an object reaches 0, Python removes it automatically. This special method dunder del is called when an instance object is about to be removed by the garbage collection. The del statement does not call this method. It just decreases the reference count by 1. This method is called only when the reference count becomes 0. This method can be used to free any non-memory resources used by an instance object. This is one method that is very rarely used. Then if you want to control the creation process of the instance object, you can define this dunder new method. This method is also not very commonly used. In this lecture, we'll see the reverse and in-place variants of these special methods for binary operators. These reverse variants have the same spellings as these methods, but they start with an R prefix. And these in-place variants start with an I prefix. First, let us see why these reverse variants are needed. We had made this dunder add method in our fraction class. And here we have put a check on this parameter. If it is an int, we convert it to a fraction and then we do the addition. So this method is capable of adding a fraction object to an integer. So we can write this. Now let us see what happens when we write 3 plus f1. This did not work because now left-hand operand is not a fraction. When this binary operator plus is evaluated, Python first checks whether the class of the left-hand operand provides a dunder add method that supports the type of the right-hand operand. Now in this case it worked because left-hand operand is of fraction class and fraction class has a dunder add method that knows how to add an int. But here it did not work because left-hand operand is an integer and int class does not have a dunder add method that can add a fraction type. If the first check fails, Python performs another check. It checks the class of the right-hand operand to see whether it provides a reverse method that supports the type of left-hand operand. So here in this case, in the next check, Python will look for a dunder reverse add method that supports an int. It does not find any, so it fails. So now let us provide a dunder reverse add method here. So this is our dunder reverse add method. In this method, we are just calling the dunder add method because this addition operation is supposed to be commutative. 3 plus f1 is same as f1 plus 3. Now let's run this. Now this worked. Let us see what is f2. So now Python calls the dunder reverse add method on this instance object f1 and passes 3 as the parameter to this method. So when you apply any of these operators to two objects of different types, Python will make two attempts to find an appropriate method. If you have an expression a plus b where a is of class c1 and b is of class c2, Python will first check if c1 has a dunder add method defined and has information on how to add an object of class c2. If such a behavior is not defined in class c1, then it checks class c2 for the reverse dunder add method. In our example that we have seen on idle, the expression f1 plus 3 is evaluated as this and 3 plus f1 is evaluated as this. If an operation is non-commutative, then by using these reverse method operators, you can define different behaviors. Now let's see these in-place methods or the augmented assignment methods. These methods are called when we write an augmented assignment statement. If an augmented assignment method is not defined, then the regular method is used. For example, to evaluate this a plus equal b, first dunder I add is checked. And if it is not there, then dunder add and dunder reverse add are considered. These methods try to modify self in place and return the result which can be self. In place methods are there so that you can implement augmented assignment efficiently if there is a need to do so. In this lecture, we'll learn about inheritance, which is an important feature of object-oriented programming. Inheritance is basically a mechanism of creating a new class from an existing class. The new class is the extended and modified version of the existing class. The main advantage of inheritance is that it facilitates code reuse. Let us understand this with the help of an example. You want to create employee objects which should have these methods and these data members. Now suppose you already have a person class that has most of the functionality that you need for an employee class. You need to add just some new things and maybe change a few things. So instead of creating a brand new employee class from scratch, you can create your employee class by inheriting from the person class. This existing class is called the base class and this class is called the derived class. When you inherit from a class, everything from that class becomes automatically available in the derived class. So here in this case, there was no need to copy everything from person class to the employee class. Due to inheritance, this employee class has access to everything from the person class. And this class can have variables and methods of its own also. So when you derive a class, the class gets access to everything from the base class. It can add new variables and methods of its own. And it can even change the way some of the methods of the base class work. For example, this contact details method that is there in the person class will be inherited by this employee class. Now suppose you want this method to work differently for the employee class. You can do this by providing separate code for it here. So a derived class can add its own version of a method. This is called overriding. The derived classes generally have some added functionality and provide more specific behavior than the base class. This base class is also called the parent class or superclass, and this derived class is also called the child class or subclass. In object-oriented terms, this relationship between the base class and the derived class is called is a relationship. Derived class is a type of base class. So an employee is a person. So by using inheritance, you can implement is a type of relationship between classes. Now this is just a simple example. The real world classes would be more complex and will have a lot more code. By using inheritance, you can use the features of a class that has already been tested and is running. And this definitely reduces effort and thus saves time. You can easily create new classes by using the tried and tested functionality of an existing class. Now let us go to idle and see the syntax of deriving a class. We have this person class with these four instance variables: name, age, address, and phone, and these three methods: greet, is adult, and contact details. Now let's make a new class named employee by inheriting from this person class. Now after this name employee, we'll write this name person inside parenthesis and put a colon here. So this line means create a new class employee that inherits from this class person. And here we write this pass statement. We have not written anything inside this class, but since it is inherited from the person class, it gets access to everything from this person class. Now let us create an instance of this employee class. Now this employee class has access to the init method of the person class. So all these arguments will be passed to this init method. And this instance object will have all the attributes name, age, address, and phone. So let us run this. So this instance object emp has all these attributes. Now let us call the methods. So we can see that the instance object of employee class has access to everything from the person class. Now let us use the isInstance function on this instance emp. This returns true. So emp is an instance of employee class. Now instead of employee, let us write person here. This also returns true, which proves the is a relationship between employee and person. Then there is another built-in function named isSubclass that can be used to check whether a class is subclass of another class. So this returns true because employee is a subclass of person class. Every class in Python inherits from a class called object. The class object is the base class for any class that you define. So this returns true, which shows that person is derived from object. All the types like str, int, ticked are names of classes. So if we write, this returns true. And here instead of str, if we write int, this also returns true. So all the classes in Python are derived from this object class. Now let us come back to our employee class and add some new methods and data members to it. First, we'll define the init method for this employee class. We need to add three more instance variables, which are salary, office address, and office phone. So we copy this init. And now we'll add the rest of the attributes. Now when we create this employee instance, we need to send three more arguments. So here we send salary 8,000 and then office address and office phone. Now let's add a new method named calculate text to this employee class. So if the salary is less than 5,000, it will return 0. Otherwise, it will return 5% of the salary. Now let's run this. This is the salary attribute. Now let's call this method calculate tax. So we got this value. So we have added a new method, and these methods were inherited from the person class. Sometimes you may want a method from the base class, but you would like it to behave differently in the derived class. For example, we want a contact details method for employee class, but we want that to have a different definition from what is there in the person class. In such a case, you can override the method. To override a method, just define a method in the derived class with the same name as in the base class. So let us override this method contact details. Here in this employee class, we want to display the office address and office phone also. Now employee class has its own version of contact details, and when an employee instance will call this method, this version will be executed. So let's call this. So this version was executed. So if a derived class defines a method with the same name, then this method overrides the method of the base class. It effectively hides the base class method. However, you can call the base class version explicitly using the base class name. So for example here, instead of copying this code from the base class, we could call the base class version here. So instead of this line, we'll call the base class method. Let's run this. In fact, here also we could do the same thing because we have overridden the init method. Instead of this code, we could call the base class init. So here we have called the init method of the person class. It takes these 4 parameters. So we have sent these arguments here. Let's run this. So if the derived class is overriding a method and wants to use the functionality of the base class version, then it is better to call the base method instead of just copying the code. This reduces code duplication, and later if the base class method changes, the change will be reflected in the derived class method also. A better way of calling the base class method is by using the super built-in function. So here you can write super. And now there is no need of sending self. Similarly, here also we can write super. Use of this super built-in function is preferred because using base class name can create confusion in multiple inheritance, where a class inherits from more than one base class. We'll see multiple inheritance in the next lecture. Let's run this. So this also works. You can have multi-level inheritance, which means that from the derived class, you can further inherit another class. For example, from this employee class, you can inherit a class called teacher and a class called accountant. So all attributes of person are available in employee class, and all attributes of employee class are available in this teacher class and in this accountant class. From person, you can inherit another class named student. Now, as we have seen before, there is a relationship between the derived classes and the base classes. So teacher is an employee, accountant is an employee is a person, student is a person, and teacher is a person, and accountant is a person. Thus, another advantage of inheritance is that you can design your system by using inheritance so that it will reflect the natural relationship between different components of your system. This simplifies the design and makes programs easier to understand. So reusability of code and being able to represent the system using hierarchy of classes are the two main benefits of inheritance. However, you should use inheritance only when there is some natural relationship between classes. Unnecessary use of inheritance can make the system incomprehensible and can create unwanted dependencies between classes. In this lecture, we will see multiple inheritance. It is not very commonly used as it can make the design quite complex and confusing. But it is good to have an idea about it as you might encounter it in some library or some other code. Till now, the inheritance that we have seen is single inheritance, which means that a class inherits from a single class. In multiple inheritance, a class can inherit from more than one base class. For example, this class X inherits from classes A, B, and C. All the data members and methods of all these three base classes will be available in this derived class X. This is the syntax of defining a new class that inherits from multiple classes. All the base classes are placed inside the parenthesis. So this statement creates a new class named X that inherits from classes A, B, and C. Here's an example of multiple inheritance. A teaching assistant is a student who teaches also. So this class teaching assistant inherits from both the classes student and teacher. Now let's go to idle and see some code. Here we have this class named teacher and this class named student, and this class teaching assistant is inheriting from both these classes. All these three classes have defined a method named greet. Then we have this instance of this class teaching assistant and we are calling this method greet on it. Since this class has its own greet method, this greet method will be called. Let's run this. So the greet method of this class was called. Now suppose this class does not define this greet method. Now since greet is not present in this class, Python will look for it in the base classes. Now both the base classes have this method named greet. So which one will Python execute? Let's run and see. It ran this greet from the student class. It is because while searching the multiple base classes, the search is performed from left to right. Let's change this order and see. Now let's run this. So now this time the method from teacher class was executed because now this is on the left. All the base classes of a class can be seen using the dunder basis attribute. So let's see all the base classes for this class teaching assistant. We get this tuple with both the base classes and the order of the base classes is the same as specified here. So this is multiple inheritance, but this is just one level deep. There can be multiple levels of inheritance. Let's see an example. This class is inheriting from these two base classes. Now these two classes could be derived from a common base class person. This is known as diamond inheritance. And we know that every class is derived from object. So this is the base class for person. So the whole structure can be quite complex, involving both multi-level and multiple inheritance. As the structure becomes complex, searching for attributes in base classes does not remain straightforward. So to resolve any sort of conflict while searching for attributes in base classes, Python uses a well-defined algorithm. The order in which Python searches for attributes in base classes is called method resolution order, or in short MRO. This MRO gives a linearized path for an inheritance structure. So Python computes an MRO for every class in the hierarchy. And the MRO is computed using the C3 linearization algorithm. This algorithm is quite complicated. You can check the documentation if you are interested in the details. But roughly it works in a depth first left to right manner. And it searches each class only once. For example, here the person class can be reached in two ways, but it will be looked up only once in MRO. We can see the MRO for any class using the dunder MRO attribute or the MRO method or using the help function. If we have an instance and want to see its MRO dynamically, we can use the dunder class attribute. Now let us go back to idle. Now we have made these classes teacher and student inherit from this person class. And all the classes have defined this method greet. Let us see the MRO for this class teaching assistant. This MRO is shown here at the top. So if we use any attribute on an instance of this class teaching assistant, first it will be searched in this class, then in student class, then teacher, then person, and then in this built-in class object. The search will stop as soon as the attribute is found. And if the attribute is not found in any of these classes, then an error will be raised. We can get the MRO in a tuple using the dunder MRO attribute on the class name. So here we got this MRO in a tuple. If we use the MRO method, we get this order in a list. So now we get a list. To find the MRO through an instance dynamically, we can use the dunder class attribute before the dunder MRO attribute. We have this instance X here. Let's use it. So again, we get the same MRO in a tuple. Now this method greet was executed on an instance of teaching assistant. And this class has its own greet defined. So this method was executed. Let's delete it from here. And let's run it. Now Python did not find greet in teaching assistant. So it searched for it in student, which is next in line in the MRO. So this method was executed. Let's delete it from here also. Next in MRO is this teacher class. So this method will be executed. Now let's delete this greet also. Now next in line in MRO is this class person. So this method will be executed. If we delete this greet from here also, let's see what happens. We get this error because next in line in MRO was object class and it does not have any greet method. So we got this error. So this is how Python looks for attributes in base classes. Although this order is called method resolution order, it holds true while searching for data attributes also. The method resolution order that we saw in the last lecture is used by the built-in function super also. This function always invokes the next class in the MRO. In an earlier lecture, we had seen that when we override a method in the derived class and need to call the base class version in that method, we could use base class name or we could use super. So here we had used super to call the parent method. In single inheritance, there's not much confusion as every class has a single parent in the inheritance chain. But in multiple inheritance, a class can have multiple parents and using super avoids all problems. Let's take an example of multiple inheritance and understand this. So here again we have taken the same example of multiple inheritance that we saw in the last lecture. We have this class person, teacher and student inherit from person, and this teaching assistant inherits from student and teacher. All the classes have defined this method greet. Now in this class we have called the parents version of greet in this overridden method. Similarly here also we have called the parents version of greet. Now this class has two parents, so we have called the greet version from both the parents. Here we have an instance of teaching assistant class and we have called the greet method on it. So this greet method will be executed. Inside this method we are executing student.greet and teacher.greet and then we are printing this statement. So first this will be executed. Now this in turn calls this person.greet. So this will be executed and then this will be printed. And then this teacher.greet will be executed, which also calls this person.greet. So this greet method from the person class will be called 2 times. Let's run this and see the output. We can see that the greet method from the person class was called 2 times. Now let's replace these base class names with super. Now let's run this. We got the perfect output and the greet from person was executed only once. This is because the function super follows MRO. Let us see the MRO for the teaching assistant class. This is the MRO for teaching assistant class. When the super function is invoked in this class, it refers to the student class because it is the next in MRO. And then here again, if super is present, it invokes this class because it is the next in MRO. And then here again, if super is present, it invokes this class because it is the next in MRO. So we can see that super follows MRO and it does not always call the parent of a class. It calls the next in line based on MRO. So we have seen how these super calls perfectly call the base class versions without any repetition. This repetition can cause real hard to find bugs when dunder init is called using base class names. Now suppose we have an instance of student class and we call the greet method on it. Then super here invokes the person class because it is the next in MRO of student class. Let us see the MRO of student class. This is the MRO of student. So when super is invoked in student, it invokes the person class because it is the next in MRO. So this method resolution is used by Python when searching for attributes in base classes, and it is also used by this built-in function super. So it is good to use super whether you are using single inheritance or multiple inheritance. In multiple inheritance, the advantage is obvious. In single inheritance also, super can be beneficial if there are some updates made in the future, like changing the name of the base class or switching to multiple inheritance. Thus, it makes the code more maintainable. The three main features of object-oriented programming are encapsulation, inheritance, and polymorphism. We have seen the first two. Now let's see what is polymorphism. The meaning of this word polymorphism is the ability to take many forms. In programming, this means the ability of code to take different forms depending on the type with which it is used. Let us understand this with the help of an example. We have this function do something that has this parameter x. Inside this function, these two methods are called on x. We know that Python is a dynamically typed language. There are no type declarations. So the type of this parameter x is not declared. We can send any type of object to this function. We could send a list object or a string object, but then we'll get error in that case because string type and list type do not support these methods move and stop. So this function will work correctly as long as we send objects of those types that support these two operations. Now let's go to idle. We have defined these three classes here. All these three classes have defined the methods move and stop, and the implementation is different in each one of them. For this class car, move prints car is running and stop prints brakes applied. For a clock, move prints this and stop prints this. And in this person class, move prints this and stop prints this. Then we have created these three instance objects, and this is the function that we have just seen in the slide. Now let's run this. Now we'll call this function do something one by one for each of these instance objects. So first we are sending this car instance object and we get this output. Now let's send this clock instance object. We get this output. Now we'll send the person instance object and we get this output. So any object that supports these two operations move and stop can be sent to this function. And the behavior of move and stop depends on the type of the object that they are operating upon. This is polymorphism. The same code can take different forms. So while executing this code, Python does not care about the type of X. Any object that supports these two methods will work regardless of its specific type. Python is not concerned about what an object is. It just needs to know what an object does. Let's see another example. We have these three classes named rectangle, triangle, and circle. And all these three classes have the methods named area and perimeter. And all of them have a class variable called name. In this rectangle class, we have these two instance variables, length and breadth, and the area is calculated by multiplying these two, and perimeter by this formula. In this class triangle, we have these three instance variables which represent the three sides of the triangle. Area is calculated using Heron's formula, and perimeter is calculated by adding these three sides. In the circle class, there is only one instance variable, which is the radius of the circle, and area is pi r square and perimeter is 2 pi r. We have created two instance objects of each class, and here is our polymorphic function. So this function takes a parameter, prints the attribute name, and calls these methods area and perimeter. Now let's run this. So first we call this function with this parameter t2, which is a triangle. So we got this output. Now let's call this function with this parameter c1. Now we got this output. Now we call this function with this parameter r2, which is a rectangle. So we got this output. So we can see that this code could take different forms depending on the type of shape. Now suppose we have a list of objects. So we have this list of these instance objects, and we want to find out the total area and perimeter of all the shapes in this list. So first we take these two variables, total area and total perimeter, and initialize them to 0. Now in this loop, we are iterating over this list and calling the area and perimeter methods on each object. And after that, we are printing the total area and total perimeter. So this is again polymorphism. Let's run this. So we get the total area and total perimeter of all the shapes in this list. Now other object-oriented languages might need these classes to be derived from a common base class to exhibit this polymorphic behavior. However, in Python, there is no such restriction. Polymorphism does not depend on inheritance. For polymorphism to occur, you just need to define different classes which have commonly named methods. Python's polymorphism is based on duck typing, which comes from the old saying, if it walks like a duck and quacks like a duck, then it is a duck. So different objects that have common method names can be treated in the same general way. Let us see some benefits of polymorphism. You can write generic code that can work with objects of different classes. When this generic code is run, Python uses polymorphism to call the correct method for each instance object. Polymorphism makes your code concise and flexible and provides a sort of abstraction. When writing the generic code, programmer need not think about the specific classes that will use the code. The code becomes very easy to update also. You can easily add new types. The functions that are already written can work with new types that you define in future as long as those new types support the required operations. For example, in future you could add a rhombus class with area and perimeter methods, and you can easily use it with the polymorphic code that we have seen in idle. Then the behavior shown by overloaded operators is also polymorphism. The overloaded operator takes different forms depending on the type it is operating upon. For example, this function can take different forms depending on the type of objects A and B. It will work correctly for objects of any type that support addition and multiplication.